session, sort of like late morning session, let us say, and we start with Federica, Gregorio, by Kolmogorov type operators, and weighted Rellich inequalities. So the floor is yours.
Thank you very much for the introduction, and also many thanks to the organizers. So I will speak about very recent results obtained in collaboration with Davide Addona from the University of Parma and Abdelaziz Randi and Christian Tacelli from the University of Salerno. And these results concerns a special class of fourth-order operators that we call bi-Kolmogorov type operators and some weighted Rellich inequalities. So we start with the outline, and we consider first the well-known second-order symmetric Kolmogorov operator, which acts on smooth functions as the Laplacian of u plus some lower-order term, which involves some measure mu. So it's gradient of mu over mu times the gradient of u. And the operator L can also be defined with via a form, which is exactly the counterpart of the associated form to the Laplacian, but with respect to the measure mu. So we have the integral of gradient of u times gradient of v with respect to mu. In order to obtain generation results for this operator, we need some assumptions on the measure. So we assume that mu is a density of a probability measure, which is locally in H1. The drift term is locally in some Lebesgue space for some index greater than the dimension, that the measure is positive on compact sets. Thanks to these assumptions, Albanese, Lorenzi, and Mangino prove that the closure of the operator L with CC infinity is the generator of a strongly continuous semigroup which is analytic and contractive on the weighted space L2 with respect to the measure mu, that we denote by this symbol L2 mu. The result also holds true in LP, but we are only interested in the Hilbert case in this talk, so we focus on L2. So our first goal, before going to the fourth order operator, is that to characterize the domain of this generator, and so to find condition on the measure mu such that this domain is exactly the weighted Sobolev space H2 with respect to the measure mu. For some special measures, this result is already known. For example, if we consider Gaussian measure, so the Kolmogorov operator becomes the very well-known Ornstein-Uhlenbeck operator, and Alessandra Lunardi in 1997 proved that, in fact, this domain is H2 of mu. Some other generalization from D'Aprato, Vespri, plus Randi, Schnobelt, show the same result for some measure with some convexity assumptions on the measure. So our first goal is to find more general assumptions on the measure mu such that this result holds. Then, in order to characterize this domain and also then the domain of the fourth order bi-Kolmogorov operator, we need, of course, some estimates that control, for example, the drift term or the derivatives of function in these weighted spaces. So to this purpose, we need some estimation and some, in particular, some weighted Ardis and Rellich inequalities. So recall the classical Ardis and Rellich inequalities. They are known since a long time. The first one was firstly proved by Hardy already in 1920 on the half line in one dimension, and then generalized to general dimension. And it states that the square of u over x squared times some constant is less than the L2 norm of the gradient of u. And this constant is the best constant and is exactly n minus 2 over 2 squared. If we want to replace here the gradient by the Laplacian operator, then there is Rellich inequality proved in 1954 by Rellich. And of course, here we have a higher order power of x. And the constant, the best constant in Rellich inequality is C0 minus 1 squared. In 219, we found some conditions on the measure for a weighted hard inequality. So we put an hard inequality with respect to the measure mu. Of course, we have to pay a price for this. So in the right-hand side of the inequality, we add, there is a DL2 norm of u with respect to the measure mu. And the constant C0 is always the optimal constant. Our second goal, so, is now to find condition on the measure in order to obtain a weighted Rellich inequality, so higher order inequality with respect to the operator L, and with some H1 mu norm of u on the right-hand side, always with best constant, which is the best constant of Rellich inequality 2. Now I define my fourth order operator, considering the form given by L of u times L of v for functions u and v in the domain of L. This form is densely defined, non-negative, continuous, closed, and so by classical result of form theory, we can associate to this form an operator, which is the generator, minus the operator, is the generator of an analytic strongly continuous semigroup of contractions in the weighted space L2. This operator, of course, is a fourth order operator, and we call it the Kolmogorov operator. And so, of course, what we want to do is also to characterize the domain of the operator, and we of the fourth order operator, and we hope that this domain is exactly the weighted Sobolev space H4 with respect to the measure mu. Finally, we know that in the context of fourth order operator or higher order operators in general, there is the lack of the maximal principle. And so the positivity preserving property of the semigroup does not hold. Already Hockenberg in 1978, studying the fourth derivative in one dimension, proved a formula for the integral kernel of the semigroup, showing that there is a cosine function in this formula. And so this kernel oscillates, and the solution cannot be positive. The ones who joined yesterday's mid-morning session in room A already heard about some resultant techniques to relax this property to a weaker property, which is more adapted in the context of a higher order operator, which is eventual positivity, so positivity for large times. Or even weaker, local eventual positivity, positivity for large times in a part of the domain. And in this context, one of the first results for the semigroup generated by the B Laplacian is from Gazzola and Gruneau in 208, and they proved that considering a positive initial datum, which is continuous and with compact support, then the solution to the Cauchy problem is locally, individually, eventually positive. What does it mean? For any compact set, there exists a time, depending on the initial datum, such that the solution to the Cauchy problem is positive for all times larger than this TK. But on the other hand, it also exists a time, depending on the initial datum, such that for any t greater than this time, there exists an element of Rn such that the solution is negative. And so our last goal is to study some parabolic properties of the B Kolmogorov semigroup in the weighted space L2. So to sum up, we have the second order Kolmogorov operator that we call L, the fourth order Kolmogorov operator that we call A, and we have four goals. We want to prove a weighted Rellich inequality in order to characterize both the domain of L and A, and then we want to study a bit some parabolic properties of this semigroup. So the goals are interconnected, so I will not go through them in the order that I presented. In fact, we will start by the last one. So recall our assumption H1, which is the assumption that we need for the generation. We know that for the Kolmogorov operator, mu is the unique invariant measure. We can prove that mu is also the unique invariant measure for the bi-Kolmogorov semigroup. The proof is simple. I can give some ideas. What we have to do is, by density, we have to prove that the integral of the semigroup applied to F in the mu, of course, is equals the integral of F in the mu for any F in the domain of A. But since F is in the domain of A, A is a generator, then we can write this expression in terms of the semigroup and the operator. Then integrating and using the Fubini theorem, we obtain that this integral is equal to this expression. But this expression is zero because this integral in parentheses here vanishes. In fact, by the assumption H1, we know that CC infinity is a curve for L, the second order operator, and the function constantly 1 is in the domain of L, and L applied to 1 is 0. But because of the definition of A, the integral of AF in the mu is exactly the integral of F1 in the mu. This vanishes. In order to obtain the uniqueness, we prove that the measure is ergodic with respect to the semigroup. So this is a first result, that the measure mu is also an invariant measure for the bi-Kolmogorov semigroup. And also we obtain some asymptotic behavior for the semigroup. We can prove that the limit of the semigroup is exactly the integral of F in the mu. This directly gives some result on the positivity of the asymptotic positivity of the semigroup. In fact, this shows, of course, if F is positive, this integral is positive, and then semigroup is individual asymptotic positive. What's more, we can prove that this semigroup is individual asymptotic irreducible, which is stronger. Taking advantage of the abstract theory, because here in this case we don't know the explicit formula of the kernel, we use an abstract theory that Sahiba explained yesterday, presented yesterday, and we can prove that if some assumptions are satisfied, then the semigroup is locally uniformly eventually positive. This assumption is some domination assumption, so there exists a natural number such that the domain of the power of A is locally in L infinity, and that 0 is a simple pole. So we give some sufficient conditions on the measure such that these assumptions are satisfied. And we have some example of measures for which the semigroup is locally uniformly eventually positive. Now, coming back to the other results that we want to prove, we have to, in order to characterize the domain, as I said before, we need the weighted Rellich inequalities. So in order to obtain these weighted Rellich inequalities, we need some assumptions on the measure, and we set this function u depending on the derivatives of mu, and we ask for some integrability assumption, the square root of mu locally in H1, the Laplacian of u locally in L1, and then we ask for x squared times u, this function, that goes to 0 when x approaches to 0, but exactly in this way. And also, we want that this function is bounded from above, away from 0. Under this assumption, the weighted Rellich inequality that I showed, the weighted Hardy inequality that I showed before holds, and then applying the weighted Hardy inequality to the function u over modulus of x, we can prove the weighted Rellich inequalities. So the assumption n greater than 5 is needed, H2 is needed in order that the weighted Hardy inequality holds. Then for any test function, these inequalities holds. They are weighted Rellich inequality with respect to the measure mu and the operator L. For the first, we only have a L2 mu norm of u, and so we lose the constant, the best constant. And for the second one, we have the best constant of Rellich inequality. And here we have this H1 mu norm of U. Some remarks now. Thanks to the hypothesis H2, which ensures also the validity of the weighted hard inequality, we are able to estimate this term. The L2 norm of U mu of the drift times a function in H1 mu is controlled by the H1 mu norm of the function. And further, if we also assume H1, which is the assumptions for generation, we know that the CC infinity is a core for L by the results of Albanese, Lorenzi, and Mangino. And then we can state that the weighted Rellich inequalities hold for all the functions in the domain of L. As I said before, the constant is the one of the Rellich inequality, and this is the best constant. We need a further assumption for this, that the drift term, the square of the drift term, is controlled by a constant over x squared. And with this assumption, we prove that the constant is the best constant. Now, in order to fully characterize the domain of L, we also need some other assumptions on the second and third derivative of the measure mu. And in fact, we ask for the third assumption, H3, 1i for the domain of L, 2i for the domain of A. So mu should be locally in W1. The derivative of the logarithmic derivative of mu should grow less than a constant over x squared plus the drift term, so the gradient mu over mu. And in order to characterize the domain of the fourth order operator, we need that mu is locally in W31, and the second derivative of the logarithmic derivative of mu should grow less than this one. So here we have a power 3. Now, thanks to the weighted Rellich inequality and the first growth assumption, so the first derivative of the logarithmic derivative, we have that if the hypothesis H2 hold, so the weighted Rellich inequality hold, and H3i hold, for any epsilon there exists a constant such that the following interpolation inequality, weighted interpolation inequality hold, and also we obtain a weighted Calderon-Zygmund inequality. This allows us to prove that when the dimension is greater than 5, and all the three assumptions hold H1, H2, and the first one of H3, then in fact the domain of L is exactly the weighted Sobolev space H2 mu with respect to the measure mu. And this is a general result on the second order operator, which is generalized some existing results in the literature. As regards the domain of A, a first consequence of this characterization is that the domain of the fourth order operator is in fact the space of functions which are in H2 mu, such that L2, L of U, is in H2 mu. In order to further characterize this domain, we need several improved weighted Rellich inequalities on several pages of computations, and then we are able to prove that if n is greater than 7, all the assumptions hold H1, H2, H3, then also the domain of A is exactly the weighted Sobolev space H4 mu. So we have achieved all the goals that we have considered. So the characterization of the domains of L and A, weighted Rellich inequality that was needed for this purpose, and also some properties of the semigroup generated by the Kolmogorov operator. As an example, we come back to the Gaussian measure. So in this case, we saw that the Kolmogorov operator is exactly the Ornstein-Uhlenbeck operator. we can also write the expression of the Ornstein-Uhlenbeck operator. In this case, it was already known that the domain of L is H2 of mu, and also we know exactly the first and the second derivative of the logarithmic derivative of mu, which are respectively a constant and 0. And so we can adapt the result obtained to this case. And this is a very special case because the domain of A is H for mu, but without constraints on the dimension. Moreover, taking advantage from the explicit formula that is known for the kernel of the Kolmogorov of the Ornstein-Uhlenbeck semigroup, indeed of the Ornstein-Uhlenbeck group generated by IL, we are also able to give an explicit formula for the kernel, or only in this special case, for the kernel of the bi-Ornstein-Uhlenbeck semigroup. And also in this case, we see that a cosine function appears. Some more general measure which we can apply our results can be an exponential with general exponent m greater than 0. And here we see that H3 is needed, especially in the case when m is in between 0 and 1 and the drift is unbounded. And for this measure, all our standing assumptions hold, and so all the results are satisfied. And also, for example, we can consider some polynomial measure with some assumptions on the coefficients. Also, in this case, the drift is singular, but all the assumptions are satisfied. And I'm finished. Thank you very much.
Okay, thank you very much. Could you stop sharing your screen?
Yes.
Okay. So, are there any questions, comments about the talk? Okay. I think Marcus, yes.
If I may, so first of all, Federica, thank you for this nice talk. I was wondering, you had quite some conditions that ensure that the domain of these operators were the one we expect. So I was wondering, are there concrete examples where the domain is something else, or?
It is not known for general Ornstein-Kolmogorov operators. We do not give some example in the other case, so we don't know. And for general Kolmogorov operator, second order, I mean, also, I don't know if there are examples. I know that it's not known in general that this domain is H2 of mu. But I don't know if there are examples of different domains. Maybe, I don't know if in the audience somebody know about it. Yeah.
So it's just unknown. Well, thank you anyway.
Okay. Can I have sort of like a related question? Because I mean, I also was struck by quite strong assumptions on the dimension of the space. So it was once it was 5, then it was 7. The question is, do you have a feeling is that it is technical assumption, and also do you have an interpretation, for example, on of the equation in R5? Let us say what, or it is just.
Yes. So the tree, you need the tree at the beginning for the R inequalities. And the 5 for the Rellich, also not weighted Rellich, the classical Rellich inequality. And then the 7 is for the, I didn't show, but I told there are some more higher order Rellich inequality that we need. And so for the integrability of the first term, you need this 7. But in fact, there are examples where you don't need, for example, as I said, the Ornstein-Uhlenbeck operator, you do not need this constraint on the dimension, because you can control the drift term and all the derivatives without these constraints. And also, for example, the measure with M So the general exponential with the e to the power minus x to the power m. When m is greater than 2, you don't have singularity. So you don't need to control the singularity with the constant over the modulus of x, because you don't have the singularity, so you don't need. So it's especially intended for general measures that also present some singularities.
Okay, thanks. Any other questions? I don't see anybody. I don't know, there are some techniques, I think, in online teaching to call students to ask questions, but maybe we'll not use. Okay, so if there are no questions anymore, so thank you very much, Federica.